Hello, my name is Arthriya Suksuwan, and I would like to present our research at University of Michigan on a robust design and optimization of stochastic wind-excited systems through an adaptive kriging-based approach. Every year, many regions around the world are affected by severe storms and tropical cyclones. Damage to structural and non-structural components have summed up to a very high economic loss. For example, the U.S. has lost almost $300 billion to wind-related events in 2017, and this is 10 times more than losses to other natural disasters combined in that year. And this has motivated engineers and researchers to find ways to improve structural integrity. However, high-performance designs are more likely to result in higher initial cost, and therefore it is also important to identify the optimal compromise between the upfront construction cost and risk mitigation. To ensure system performance, performance-based design approach can be used to evaluate system performance in terms of expected loss and variability in the system level loss, which is the indication of robustness of the system. At the same time, optimization technique can be used to identify feasible designs with a minimal upfront cost. And this has brought us to the proposed design framework that is based on integration of performance-based design methods together with optimization technique that can handle multiple objectives, uncertainties in the systems, and a large number of design variables. And due to the conflicting nature of the initial cost and anticipated loss, it would be very useful for decision makers to see the complete picture of trade-offs through the Pareto optimal solutions. Hence, it is of interest here to solve optimization problems in the multi-criteria setting. The multi-criteria optimization problem may be formulated as follows. X is a high-dimensional vector that collects design variables such as member sizes. V denotes the cost function, which may be taken as structural material volume. L represents loss measure, defined here as the combination between the expected value and the standard deviation of the decision variable, such as the total repair cost. A parameter alpha is introduced here as a robustness parameter that allows decision makers to choose the level of robustness that they prefer. The higher value of alpha results in tightening the variability of the system level loss and therefore leading to a more robust design. To estimate the expected value and standard deviation of the system level loss, performance-based wind engineering frameworks can be used. Starting off with identifying the intensity measure through the hazard analysis, then we perform aerodynamic analysis to estimate the wind loads on the system, followed by structural analysis to estimate the responses and engineering demand that will be used in identifying damage to the components in the system. And by summing up all components' repair cost and time, the total repair cost and repair time can be estimated. This allows us to estimate the system level expected loss as well as the standard deviation, which tell us how the total loss varies around its mean value. It is also important to account for all uncertain parameters involved in all analysis steps. And together with stochastic wind load, these integrals can end up having thousands of dimensions, and therefore, it is proposed here that they should be solved using numerical simulation. This optimization is very challenging to solve because not only it involves multiple objectives, but also one of the objective functions is in terms of the probabilistic loss measure that requires a time-consuming simulation. And for practical system, X is also high-dimensional. To solve this problem, we first decompose the original multi-criteria problem into a series of single-objective optimization problems through the epsilon constraint approach. For each epsilon constraint problem, the simulation-based performance assessment is nested within the optimization process, so it is still time-consuming when we have to carry out a Monte Carlo simulation for every candidate design. To efficiently solve this single objective problem, we would like to decouple the simulation from the optimization process through defining an approximate optimization subproblem. In particular, we would like to have a computationally cheap approximation scheme to estimate the loss measured as the design changes. To do so, it is proposed here that the problem can be divided up into 3 steps. The first relates design variables to the mean and standard deviation of the engineering demands, which are then related to the mean and standard deviation of the loss in the corresponding performance group, which will be referred to here as the group level loss. Then the mean and standard deviation of the group level losses are related to the expected value and standard deviation of the total loss of the system. For the first step, let us consider the simulation in the current design point. For a given realization of uncertain parameters, we can generate a sample of response process, a sample of engineering demand, and also a sample of vector value stochastic process. Based on these samples, we can define the following probabilistic variable, which can be used to estimate the auxiliary variable vectors, or the AVVs, as the byproducts of the simulation. The interest in estimating these AVVs is that when they are statically applied to the system, we obtain the response exactly in terms of the mean and standard deviation of the engineering demands. This is an exact relationship that is explicit in X and requires a simulation only in the current design point. Second step, to relate the second-order statistics of the demands to the second-order statistics of the group level loss, we observe that from the simulation in the current design point, we have samples of engineering demands which can be manipulated through the following transformation to obtain a new set of samples with the corresponding mean and standard deviation that we are interested in. We can use this new set of demands and perform only the damage and loss analysis again to generate a new observations of the mean and standard deviation of the group level loss. After collecting some observations, the creaking models can be constructed that can predict the mean and standard deviation of the group level loss in the space of the mean and standard deviation of the demands. And last step is to connect the group level losses to the system level loss. Because total loss can be written as the summation of component losses over all performance groups, so the expected total loss can be calculated as summing all mean values of the group level losses, while the standard deviation of the total loss can be calculated in terms of the correlation coefficient and standard deviation of the group level losses. And from here, we can substitute in the creaking models to quickly approximate the expected value and the standard deviation of the system level loss. Now, if we assume that the AVVs and the correlation coefficients between group level losses are independent of changes in X, then the probabilistic analysis is decoupled from the optimization process, and therefore, the original epsilon constant problem can be solved through a sequence of static, simulation-free optimization subproblems. In particular, gradient-based algorithms can be used here. To quickly test the potential of the proposed approach in solving single-objective optimization problem, the test problem here is to design a two-story frame which consists of 4 design variables, 2 performance groups, with each group having 32 cladding components that are susceptible to peak story drift ratio, and have 3 possible damage states. The frame is subject to stochastic wind loads that were generated using the quasi study wind model, with a wind intensity measure taken as the wind speed with the mean recurrence interval of 1700 years. The performance objective here is to ensure that the sum of the expected value and standard deviation of the total cost does not exceed $50,000. We apply the framework and obtain the following result. An example of creaking model is presented here, showing the global approximated surfaces of the mean and standard deviation of the group level loss and how the regions where optimal solution exists are quickly identified within the first cycle. The accuracy of the approximated expected value and standard deviation of the total loss is shown to be very accurate throughout sequential updating. The objective function is minimized with the smooth and steady convergence properties, while the constraint satisfies its target within the first few cycles. This strongly demonstrates the potential of the framework. To investigate the applicability to multi-criteria optimization problem, a case study is carried out on a large-scale system that consists of more than 250 design variables. 37 performance groups of cladding components susceptible to maximum peak story drift from along wind and across wind response processes. The system is subject to stochastic wind loads that were generated based on wind tunnel-informed POD model. The optimization goal here is to obtain Pareto optimal solutions for minimizing structural volume and loss mature. In formulating the epsilon constraint problem, 5 loss threshold values were considered and 3 levels of robustness were investigated through varying values of parameter alpha. Therefore, a series of 15 single-objective optimization problems were solved through the proposed adaptive kriging-based approach. And here are the results. The first figure shows sets of Pareto optimal fronts in the space of the two objectives. As expected, anticipated wind-induced loss is higher for systems with lower initial cost, and a higher initial cost is required if a higher level of alpha is chosen for a more robust design. Moreover, results from the Monte Carlo simulation carried out for each of the optimal points can be used to estimate the associated probability of exceeding a given loss threshold, as illustrated in the second figure. This not only provides a more complete picture of the system performance, but it also provides a means for decision makers to identify which value of alpha to consider in order to choose the optimal trade-off solution. For example, if the stakeholder is interested in the optimal design that has the probability of having loss mature exceeding $50,000 to be less than 0.01, the corresponding alpha value is interpolated to be around 1.65. An additional single objective optimization can be carried out to obtain the corresponding optimal design. Regarding the effectiveness of the proposed adaptive kriging-based approach in solving large-scale problems, similar to the small case, the optimal design is obtained with the steady and smooth convergence of the objective function, while the system-level constant was satisfied within a few cycles. Approximation of system-level loss mature is shown to be very accurate, especially after constants were satisfied. And this truly highlights the scalability of the proposed method. To summarize, a performance-based design optimization framework is proposed that is capable of handling multiple objectives with one objective defined in terms of loss mature that accounts for both the expected loss and also the robustness of the system. A decoupling strategy was presented that was based on defining simulation-free optimization subproblems through the use of AVVs and the kriging metamodels that constructed in space of the mean and standard deviation of the engineering demands. And lastly, the applicability of the proposed framework was demonstrated through the optimal designs of both small-scale and large-scale building systems subject to stochastic wind loads. Thank you so much for your attention.